Hello and welcome to MOOC on optical communications. We were describing in the earlier module the role of DSP in optical communications. We will continue the discussion. First, we will concentrate on compensating the chromatic dispersion that exists in the fiber. Okay? And to do that, what we will do is to go back to this picture where we recognized that if you take the Fourier transform of the envelope function that you are transmitting, which would be modulated envelope function of course, that can be represented as a linear transformation because you have a fiber transfer function hf of omega, which is given by e power minus j beta 2 z by 2 omega square, right. Now, what we have at the output of the coherent receiver followed by ADC and everything is the sequence of samples Rk, right. So, these are the sequence of sample values that I get Rk, which then has to be applied for a frequency, I mean it has to be sent in through the compensator for CD, right. Where do you get these CDs? These Rk are the result of after propagating through the fiber. So, this is where you get the samples Rk, or equivalently if you are still thinking in terms of the continuous time functions, you started off with some a of 0 omega here, and what you got here was a of z omega, which would not be equal to a of 0 omega. Okay. This is I am giving you the continuous time idea so that we can later go to the discrete time ideas. Okay. So, if you start with a continuous time signal with an envelope function a of 0 t, then go to the Fourier domain, get to a of 0 omega, propagate through the fiber by multiplying it through the transfer function. Now, you are at this point a of z comma omega. What you now do is, now you have to pass it through a different filter. Okay. If imagine that you are doing everything in the analog domain. So, in this analog domain what you have to do is this received signal, which would be some photocurrent but varying as a function of a of z comma omega, will have to pass through the the filter such that the output would be a of 0 omega again, right. This is a very simple idea, right. I mean you send something, it has got modified, that modifications have to be removed. So, whatever the changes that has happened in the frequency domain has to be undone by another filter. So, we are assuming that this fiber transfer function hf of omega is kind of an analog filter. So, what you have to do is to put another analog filter whose frequency response must be in such a way that the combined frequency response of the fiber and this filter must be equal to identity, correct. So, if I multiply hf of omega, which is the fiber transfer function, right. So, if I pass it through, so this is the input that you are giving to the equalizer filter, as we call this one. So, the second filter or the equalizer filter will multiply by h equivalent equalizer of omega. This is the transfer function of the second filter or the equalizer filter. But we know that two filters in cascade means that their corresponding transfer functions multiply each other, right. In terms of convolution or in terms of time domain, there is convolution happening, but in terms of this picture there is multiplication happening. So, when you multiply the transfer functions, what you get is a of 0 omega, hf of omega, h equalizer of omega. This must be equal to a of 0 omega back, or if you want you can multiply this one with certain scale factor k. So, some amplitude times a of 0 omega is what you should expect. So, which means that this fellow must be equal to k times I, where I is basically the identity function. So, which again means that the transfer function h equivalent h equalizer of omega must be the inverse transfer function of hf of omega. What would be the inverse transfer function? What if you multiply this one with the fiber transfer function h e power minus j beta 2 z omega square by 2 will give you 1. What would give you 1? Obviously, instead of having e power minus j beta 2 something, you simply have a e to the power plus j beta 2 z omega square by 2, okay. Because if you multiply this one with the fiber, what you are going to get will be plus 1. So, it is like you have a fiber which is characterized by beta 2 and then you propagated this input to this one at the output, you now have what I would call as a virtual fiber, okay. So, this is the real fiber to the left I have, and this is my virtual fiber. It is kind of a fiber that does not really exist, but this is something that is actually the analog filter transfer function that I am using, and this virtual fiber will be characterized by minus beta 2. So, if there is a normal dispersion going on with a positive beta 2 for the regular transmission fiber, you simply put a fiber with a minus beta 2 term, that is the sign of the dispersion coefficient reverses. Beta 2 positive means negative d, beta 2 negative means positive d, because beta 2 is related to d. The dispersion coefficient is given by minus 2 pi c by lambda square into beta 2 is given by the dispersion coefficient d, correct. So, if you were to put in a virtual fiber in the DSP domain, then you are going to undo whatever the effects that the transmission fiber has done, fairly simple. However, how do I implement this in the DSP domain? Well, we will come back how to exactly get the discrete time version of the transfer function correctly, but for now what we need to do is, my received symbols are Rk. What I do is I take an n point, I group them, this Rk I basically group them into n symbols, okay, such that I get say Rk, Rk minus 1 all the way up to Rk minus n plus 1. So, there are about n samples that are there here, and what I do is, after taking this n samples, so I convert them from a serial to parallel conversion, right. So, this is a serial to parallel conversion. What I do is I simply take the Fourier transform, right. After taking the Fourier transform, I then put my H equalizer of omega, omega being the this one, right. So, I will put down this as H equivalent of m, right. So, this will be my Fourier transform multiplied by H equalizer, which is again the Fourier transform with a sign of minus beta 2 here. The output will be the Fourier transform A of z omega. So, I will again put my parallel to serial block back, and then I get my Rk values. Okay. So, this is one way of performing equalization using DSP, and this is called as frequency domain equalization. I have given you the barest ideas. There is actually a lot of work that needs to be done in order to properly implement H equivalent of m, whether it is even realizable, whether it is causal, stable, all those considerations are there, which I have kind of avoided in this discussion, but this is the basic idea. Take the input signals, take the FFT of them, pass it through the H equalizer. You have to go back to the IFFT. So, I forgot to put the IFFT over here. After parallel to IFFT followed by parallel to serial, and then get back to your Rk. Okay. This is the compensation in the frequency domain. Now, you can go back to time domain and then perform a time domain equalization. In the time domain equalization, all my input signals Rk will be appropriately delayed. So, you get Rk, Rk minus, you get a chain of these values. So, you get Rk minus 2 and so on. The output of each of them will be multiplied by a certain weighting function. So, this is actually some W0, this would be multiplied by W1 and so on. So, this would be multiplied by W of m minus 1. So, where m is the length of the filter that we have taken, and the output is all combined. Okay, the output is all combined here to give you the value of Rk. So, here this would be Rk minus m plus 1, I suppose. So, this is again obtained by all the delay elements. So, this Z inverse stands for delay. So, one element delay you are going to get this thing, right. So, this Rk hat, which would be the Rk, is supposed to be the equalized version of Rk. Now, what are these W0, W1, Wm minus 1? These are nothing but the coefficients Hf of n. Okay. Remember, we had the fiber transfer function. From the fiber transfer function, we went to the impulse response, and the impulse response we sampled it in order to generate this Hf of n. Okay. So, if this is a m length filter, then you actually get Hf of 0, Hf of 1 and so on. Instead of writing Hf of 0, because the space constraints would not allow me to write correctly, I renamed Hf of 0 as W0, Hf of 1 as W1 and eventually Hf of m minus 1 as W of m minus 1. Okay. So, these are the same impulse responses. Now, here is a catch. What value of m should I choose? Unfortunately, the value of m that you have to choose depends on the length of the fiber that you connect. You know that as the length increases, the total term beta 2 into L will also start to increase. The pulse width will increase by beta 2 into L. So, the larger the value of L for a fixed value of beta 2, the larger will be the term beta 2 into L. So, one has to include, so if you start with 100 picosecond pulses and eventually you are going to get pulses of 1 nanosecond after propagating through a length of L, then one has to include sufficient number of taps such that the pulse after propagation, or you have to mimic with a certain number of taps such that the number of taps should be such that the output would have been spread to 1 nanosecond. So, there is actually a 10-fold increase in the pulse width, and you have to include a sufficient number of values of the m or the values m in order to capture this effect correctly. There is one more catch here. We have assumed, or the way we have written here does not really account for pulse spreading in the backward direction. I mean, the pulse is basically spreading in both directions, right. So, one way normally people account for this is, in the frequency, in the time domain equalizer, is to not just consider the present symbol Rk, they will also consider the future m symbols and the past m symbols, because they assume that the result of Rk is actually affecting the future m symbols, because there is a pulse spreading in this direction, and it has also been affected by the past m symbols because of the previous one. So, you go from R of k minus m minus 1 all the way up to Rk plus m minus 1. So, there is a total of 2 m plus 1 length tap filter that you have to consider. So, which means that the corresponding W's will also be W of minus m minus 1 all the way up to W of m minus 1. So, total of 2m plus 1 tap filter is to be considered in order to obtain the proper representation for the pulse spreading or for the intersymbol interference effects. Pulse spreading gives rise to intersymbol effects. So, you assume future m samples are corrupted, you assume past m samples are corrected, and you put your equalizer in such a way that the present symbol is actually corrected version. How do you get the future symbols? Well, you have to put them through a buffer and store it. Okay, it is not future per se. It only means that you have to have 2m plus 1 samples available with you. So, if when you are processing the sample on a computer Rk, it is easy simply to access this particular array, right. So, you think of this Rks as imagined inside of an array, which is 2m plus 1, and the inputs are getting pushed out in this manner. So, as the input comes in, the inputs go out. So, if you are looking at a particular kth output, you have to consider the previous m and the next m. So, the entire array you have to consider, convolve that with this one. Okay. Now, how do I convolve something in the time domain? Well, if you go to the convolution theorem with this one, you can implement convolution in the time domain, but it is actually easier to implement convolution in the frequency domain using FFTs. So, what we do is again go back to the FFT kind of an idea, provided you want to use FFT. If you do not, you can always use a time domain convolution thing, which I just described in the previous block, right. So, that diagram was actually for the time domain convolution. You can easily do the time domain convolution, but if you want to use FFTs here, you then go to the implementation of convolution, linear convolution using FFTs, which means you have to basically use overlap save or overlap add methods in order to implement those convolutions, right. So, you can do that in the frequency domain, but if you want to stick to the time domain, this is the equalizer filter that you have to perform. So, you have to consider, so these W's are actually from the, not from the filter, I am sorry, these are actually from the equalizer, because the fiber has already gone. What you are now doing is the equalizer. So, from the equalizer transfer function you have to do this one. What is the equalizer transfer function in the time domain or equalizer impulse response? It is e to the power t square divided by j2 beta 2 into z. So, the equalizer transfer the function will be e to the power minus t square j2 beta 2 z. This has to be sampled. Okay. This has to be sampled, and when you sample it, you are going to get e to the power minus j n square ts square. So, this is for the fiber. When you sample this, you are going to get e power minus j n square ts square 2 beta l, and the idea is that if you have a sampling rate or the Nyquist rate of Rs, then we know that if you have a Nyquist rate of Rs, then the maximum bandwidth that you can represent with this Rs will be Rs by 2, correct, or equivalently if your signal is band limited to B, then the Nyquist rate Rs must be equal to 2 times B, and Rs here is given by 1 by Ts, where Ts is the sampling time. Okay. So, let me write down this as 1 by T samp. Okay. So, this sampling rate you have to choose such that you convert Hf of t into appropriate Hf of n. Similarly, you convert H equivalent of t, which is the Fourier transform or the inverse Fourier transform of H equivalent of omega, I am assuming that there is only going to be a sign change there, right, and this has to be converted to H equivalent of n, which is nothing but all the W n's that we have looked at. So, all the W n's that we used in the time domain convolution are actually coming from this H equivalent of n. So, what should be the number of things that I have to include? What is the maximum bandwidth that I can get to? The maximum value that I will get will be given by, so if the number of taps we have considered is m, so it would be m Ts divided by 2 pi beta 2 L will be the max frequency component, correct. Why would this be the max frequency component? Because my m is going to go up to there and frequency is obtained by differentiating the phase term. So, phase term is t square divided by 2 beta 2 into z something. So, differentiate that one with respect to time, you get 2t in the numerator. So, you get t by beta 2 into L, right, and this is 1 by 2 pi will give you the frequency f rather than omega. So, this would be the max frequency, and when you let t is equal to m into t sample. So, let us write this m into t sample, this is the maximum time t that you are considering. So, which means this would be the maximum frequency that you are considering. Okay. So, this maximum frequency should be in such a way that Rs should be such that Rs should be greater than or equal to 2 times this maximum frequency component, right. So, it must be greater than 2 times this maximum frequency component, and you are going to get Rs greater than or equal to 2 times this. You can cancel off 2, which means that m has to be greater than or equal to a value of pi beta 2 magnitude L divided by t sample square. Okay. You have to choose this to be appropriately such a length. Typical values of m turn out anywhere between 17 to 23 with an acceptable performance. Okay. So, once you have done that one, you replace all the W n's by H equalizer of n values, okay, and after you have done this replacement, you go back to this transfer function here and you feed in all the received RK values into this filter, and you are going to get W0, W1, I mean you are going to get the output RK, which is an equalized version. There is an important point here. If you fix all the values W0, W1, Wm minus 1 as constants, then you get what is called as the static CD compensator. Okay. So, if you fix this, you get what is called as a static CD compensator, but if you pick some of these terms, like let us say I pick some of these terms and then make them vary, I vary the coefficients W. So, when I vary these coefficients, I am doing what is called as the adaptive equalizer. Okay. When I do adaptive equalizer, so basically what I do in the dispersion compensation is that I split this m. So, let us say m is equal to 23. What I do is I split this value of m into 2 portions. So, let us say m1 and m2. So, the m1 coefficients are going to be static, okay, and m2 coefficients are going to be adaptive or varying. And how do I vary or how do I update the coefficients? One of the most famous rules for updating the coefficients from one time step to another time step is basically this is the new value, this is the old value plus mu error that you have committed at that particular time and dk of n, where dk is the desired response and E is the error between the desired response and the actual output. Okay. So, this rule is called as the least mean square algorithm, or this method is called as the least mean square algorithm. You can learn about this least mean square algorithm in other courses, and if you use that, you are updating this m2 coefficient. So, if it is 23, maybe you put about 18 coefficients here and you put about 5 coefficients here, and they should be all right. People have also experimented with putting m minus 1 static coefficients and 1 adaptive coefficient, so that you have a total of m taps to vary. So, this is one adaptive coefficient is also people have tried. Anyway, so this is about how to perform CD compensation. So, you actually perform CD compensation by splitting this into static and dynamic equalizer. The static equalizer comes from the equalizer outputs or the equalizer impulse response. You can perform equalization of or you can perform CD compensation either in the time domain or in the frequency domain. You can perform adaptation both in time domain as well as in the frequency domain. What is the next thing that we want to consider? What we want to consider next is the phase noise compensation. Again I will go through basic ideas of phase noise compensation or phase noise estimation. Much more algorithmic details can be found in the recent literature. The basic idea here is that you start with Rk, Rk is given by Sk e power j phi k plus Nk. If there was no noise, then things would have been very simple, because this phi k we are going to assume that there is only phase noise. Okay. Sk unfortunately is non-known to me, but let us assume that this is equal to 0 for now. For now we will assume that there is no noise. How am I going to estimate phi k? Well, you might say you take Rk and then you multiply this one by Sk complex conjugate. When you do that, what you get here is magnitude of Sk square e power j phi k. What is magnitude of Sk square? If I were to consider a QPSK system, right, then the magnitude of each of these components is equal to 1 after normalizing. They all carry same power, therefore, if I take the magnitude square, all of them will have an equal power, and if you normalize them, this will be equal to 1. So, you get Rk Sk complex conjugate is equal to e to the power j phi k. Has it solved our problem? Yes and no. Yes, because this is a equation that can be solved, right. So, if you now take the argument Rk of Sk complex conjugate, please note that this is a complex number, this is also a complex number, you have to take the argument of the complex number. If you take that, you are going to get phi k, or at least the estimate of phi k. Fairly simple. The only trouble is the argument function will always return the values between minus pi to plus pi. Okay. If the actual phase happen to be some pi plus delta, then this pi plus delta will be folded back into minus pi minus delta. Okay, it would be or minus pi plus delta, I am sorry. So, it would be folded back, because the argument function of any trigonometric function is either from 0 to 2 pi or from minus pi to pi, because it is periodic in time, right. But if the actual phase is now the phase that is coming from somewhere, right. So, the actual phase is kind of the time delay can go beyond 2 pi. The problem is this kind of a phase, which is called as the unwrapped phase, will become wrapped phase. So, it is kind of taking it and rounding onto a cylinder. So, if you am looking at pi, so if this is minus pi and pi which are coinciding with each other, if my phase happens to be pi plus delta, that actually shows up as minus pi plus delta. It is actually a bad thing, right, because now your phase is getting wrapped and someone has to unwrap the phase, right, and there has to be algorithms that are developed to unwrap the phase. Okay. So, even as simple idea as this with no noise must be accomplished or must be accompanied by an unwrapping phase process. Okay. One has to unwrap the phase. Now, this is not just the only problem. Suppose now noise is non-zero, right. Suppose noise is non-zero. What will happen now? The resulting arguments of Rk Sk complex conjugate, you can still do this. This is going to be e to the power j, sorry, not the argument. Let us just look at e to the power, the expression e power j phi k plus some Nk prime, where Nk prime is equal to the original noise sample Nk multiplied by Sk complex conjugate. Okay. So, there is going to be this noise term. Fortunately, we are assuming noise to be not very high. So, if the noise variance is small, then I can represent this entire thing, or I can take this e power j phi k and write this as Rk Sk complex conjugate minus Nk prime, and then take the argument of phi k. So, if I take the argument again, I am going to get argument of Rk Sk complex conjugate minus Nk prime. Okay. Of course, it is not really going to be this way, you have to first convert this into the polar form. So, when you convert this into the polar form, you are going to get phi k plus phi Nk prime and Nk prime magnitude. Okay. And what you have to do is to extract this, you have to equate this one to Rk Sk complex conjugate. Okay. And in case the noise sample, it is noise, right. So, this noise sample becomes equal to 0, then you are in big trouble, because you can't really estimate this phi k there. Okay. So, there are things that you have to take care of. The second thing is that it is possible to show that these Nk primes are still going to be 0 mean processes. Okay. And you now have, instead of dealing with only one sample value phi or Rk, what you do is you deal with m sample values. So, Rk, Rk minus 1 all the way going back to Rk minus m plus 1, that is you go to m samples previously and you take all these m samples, find out the corresponding phi k estimates. Okay. Take phi k minus 1 estimates and then take phi k minus m plus 1th estimate and then combine these phase estimates. Okay. So, if you combine these phase estimates, you are basically doing some averaging effect. Okay. So, you have Sk complex conjugate Rk with whatever minus Nk prime that you have. So, take the sum of these over k is equal to the present value of k2, k is equal to k, or rather some dummy variable from k is equal to n to n minus m plus 1, and then divide this one by the block length 1 by m, and what you get is the average phase phi k over the entire m samples. Okay. So, if you what you are doing is finding out the average phase phi k at the kth time based on moving average m samples, moving average m sample or m window function. So, you can do this, and you can also multiply it by other smoothing functions in order to better perform the averaging process. So, when you do that, you are going to get an average phase estimate, and this is all right. Why is it all right? Because the data rates is actually at around 100, data rates are, let us say 100 Gbps corresponding to about 100 picoseconds, or 10 Gbps corresponds to 100 picoseconds and 100 Gbps corresponds to 1 picosecond. So, your time variation, the symbols are varying at 1 picosecond sampling time, right. Compared to that, the phase noise is a much slower process. So, the phase noise can be assumed more or less constant or varying very slowly over a block of m samples. Of course, if you make the value of m very large, then you are not going to be doing a good job, because you are assuming that the phase noise is almost constant over a large block, which is not correct. But if you make m to be very small, then you are updating frequently, which is also not, which means that you do not give time for the noise to settle down, right. So, noise has to be averaged out, which means you want a optimum value of m, and people have looked at what happens to the performance of the systems provided or as a function of how we change the value of m. Okay. There is an optimum value of m for which the performance is kind of better. If you start making m very large, the performance degrades. If you make m very small, then your noise does not get really averaged out. So, this is how you perform phase noise estimation. There is one last topic about our nonlinear DSP in optical communication, which is the nonlinearity mitigation. We are going to discuss nonlinearity mitigation in the next module. For now, this is the algorithms that we have discussed, and I will give some recent papers in the course website for you guys to have a look at these algorithms. Thank you very much.